So in the previous lectures, we discussed about common source, and common drain amplifier. If you see, both common source and common drain amplifiers are fundamentally power amplifiers. They draw very little to no power from the input, but they deliver a finite power to the output. Therefore, we said both these stages, both common source and common drain, offer a huge power gain. And we said that's the definition that distinguishes active devices from passive devices. So for example, I had already given you guys an example. So if I had taken a transformer, a 1:n turn transformer, 1:n turn, we said if I apply an input voltage V1, the output voltage will be n times V2. It's a lossless transformer. This is the voltage you will be delivering to the load. But the thing about the transformer is that even though voltage increases, current scales down by the same factor. So that the total power you deliver to the load, the total power which you deliver to the load will always be less than or equal to the input power. For ideal lossless transformer, input power will be exactly equal to the output power. Output power will exactly be equal to the input power. But in practice, if there are some losses, in the transformer, your load power will be always less than the input power. That's one problem with, that's one distinguishing feature of a passive device, which I'm using the word passive. A passive device or a circuit cannot amplify power. An active device can amplify power. So that is why, even though common drain configuration, we just took an example and we said, even though you had a common drain configuration, it was, the voltage gain was just one. The voltage gain was just one, but we still call it as an amplifier because it provides a huge power gain, because the current gain is infinite. Okay, so you can also define power gain as the product of voltage gain into current gain. AI is the current gain, AV is voltage gain. So what is the voltage gain of a common drain amplifier? Approximately what would it be? Yeah, that's the intrinsic gain. Approximately it's 1, right? Voltage gain is 1. It will be less than, I can say that AB is always less than or equal to 1. It's actually less than 1. What is the current gain of a common drain amplifier? Current gain is the input current, output current, I out, or load current divided by the input current. What is that? Current gain, input current is 0 always. There is no current drawn from the input. Still, you are able to provide some finite current at the output. So therefore, the current gain is infinity. So when you look at power gain, the product of current into voltage, it's extremely large. It's close to infinity. In reality, probably some of you might have already done your lab assignments. We will have some bias resistance, which will be used for biasing. So I'm drawing the small signal model here, so I have not shown the capacitor. So usually you might have some bias resistor, which will absorb some current from the source. It will absorb, it's not that source will not provide any current at all. It will absorb some current from the source. This means there will be some power. So Vs into II is the power drawn from the voltage source. You are going to draw some power from the voltage source. That's something you will always do. Still, what we are saying here is that the load power that you are going to deliver will still be much greater than the input power. So I just took an example. I showed here that the input power drawn is 0 because no current is being drawn. But I said in practice, you might have some bias circuitry. That bias circuitry might draw some power. For example, I've assumed yesterday I discussed a problem where you had a base resistance, a bias resistance RB connecting to a DC voltage source VB, which was used to set the DC voltage at this point. Now, for AC analysis, I can assume the DC voltage is a short. So if it's a short, then what we are saying here is that you will still be drawing some input current. You will be drawing some input current from the voltage source PS. In that case, I can argue that maybe the input power is finite, but it's still much smaller than the power you are going to deliver to the load. Which is why I can say that this is going to have a huge power gain. The amplifier is going to give you a huge power gain. So by that definition, even though voltage gain is just 1, we will still call a common drain amplifier as an amplifier. Now finally, I've left out one final amplifier configuration. Okay, so one of you are asking, what about the power gain of a common source amplifier? Well, let's look at a common source amplifier. this is your load resistance. So your power gain is simply the voltage gain times current gain. What will be the voltage gain of a common drain amplifier, a common source amplifier? Typically voltage gain, if let's say I connect a load resistance RL in parallel, imagine there is an R0 in parallel with it, what will be your voltage gain? Can you say intuitively now? You have a current minus GMVI flowing here, minus of GMVI, minus of GM into R0 parallel RL. This is the voltage gain of a common source amplifier. This, and what is the current gain? Let II be the input current. What is the current gain? I out be the current flowing through the load. What will be the current gain? Infinity, right? Current gain will be infinity. So your current gain is infinity. So common source amplifier is the only amplifier which will give you both current and voltage gain. It will amplify both. So the power gain will be really very high in case of a common gate amplifier. In case of a common drain, voltage gain is not very high, but current gain is very high. In case of a common source, both are very high. Both voltage gain and current gain are very high. So that's why this in fact the power gain will be highest for a common source amplifier. For lower frequencies, this will be the highest for a common source amplifier. Okay. So I think one of you are asking, how is current gain infinity? Because the input current drawn is 0. So output current gain is IL by II, which is infinity. Yeah. Okay. So now I'll start with our discussion on the third amplifier, which is a common gate amplifier. We will see that when we are doing the analysis of common gate amplifier, it has some drawbacks, and the mathematical analysis of common gate amplifier is a little bit more complicated than common drain and common source. But we will make some approximation and understand a common gate amplifier, and you will also see its advantages and its limitations. Therefore, by in itself, if I want amplification by in itself, I may not prefer to use common gate, but in some specific applications, we can use common gate as an amplifier. So I will talk about all of that. So in a common gate configuration, so we have discussed two common terminals, so which is common source and common drain. The third is a common source topology. Now, again, I told you guys, whenever you define a common terminal, you have to define the input and the output terminal as well. That's when completes a three-terminal MOS amplifier structure. So now, let's define source as the input and drain as the output. Now, as I vary the source voltage, as I vary input, what should happen for an amplifier? You should have either the output current changing or voltage changing. Either one of them will lead to, voltage. If current is changing, then that will also lead, we can also say the voltage will also change if I connect a load resistance here. Now analyze the circuit intuitively. If I change VI, the load current here is I0. I0 is the output current. Is there a relationship between I0 and II? Is there a relationship between the input current and the output current? Ignore R0 for the time being. Is there any relationship between input and output? Yes, right, they both are exactly the same. For a MOSFET, the source current is exactly equal to the drain current. So what I'm drawing here is small signal currents. So your I0 is exactly equal to II. So can you say what is the current gain of a common drain amplifier? If I ask a common gate amplifier, current gain is 1. So the current gain of a common drain amplifier will be approximately 1. Now, if I change my input voltage, will II change? Can you give me an expression now that you know to analyze at least to a circuits to a decent level? If I change my input voltage, what will be the change in II? See, what is VI? VI is nothing but minus VGS. Okay, this is minus VGS. So think what will be II in terms of, no, look at it, small signal wise. VI is a small signal voltage. Yes, so it will be VI is a small signal, VI is a small signal voltage. That's what is VI? VI is minus VGS. And what is II? II is minus drain current. Drain current, small signal drain current is assumed to be flowing from drain to source. So therefore, ID is nothing but GM/VGS. And if I substitute ID as minus II, you get GM times VI. So II is in this direction. So II is simply GM times VI. which is also equal to I naught. So your I naught, if you see the output current, is actually proportional to the input voltage. So yes, this will work as an amplifier, because for it to work as an amplifier, either the output current or voltage should change in proportion to the input voltage or input current. Both either one of them should it happen, and it's changing with respect to the input voltage. Now, if I invert the terminals, do you think it's going to work? Let's say I just apply my input at the drain terminal, and I'm going to take my output at the source terminal. Let's ignore channel length modulation for the time being. If I ignore channel length modulation, even if I change drain voltage, will there be any change in the drain current? Assume the device is in saturation region. Look at the IV characteristics of a MOS device. The IV characteristics look like this. In this region, even though VDS is changing, there is no change in the drain current. Drain current remains constant to first order, but usually there will be some R naught, because of which there will be a change. So you cannot use it as an amplifier in the direction. Now let's assume that there is some R naught. If there is an R naught, yes, there will be some change. Because of R naught, there will be some current flowing in the input terminal. Okay, so you will have some. No, the device is not. See, understand. See, I think one of you are asking a question. Isn't a device? Isn't it a symmetric device? But you should understand the symmetricity will hold true. I mean, sorry, the idea of being symmetric will hold true only in digital design. In analog design, once you bias a transistor, drain voltage, once you bias a transistor, drain voltage will always be greater than source voltage, which means drain is fixed, source is fixed. In digital circuits, it is interchangeable. Analog circuits, if and only if you are using a MOS device is in linear region, where you are going to use it as some kind of a switch in analog circuits, it is interchangeable. But in an amplifier, it is very precisely defined. Drain will be at a higher potential than the source. Yeah. So this is drain, and you will still have some feeble current because of R naught, and we will calculate what will be that gain as well. At a later stage, we will see what will be that gain as well. Okay, so one of you are asking what happens if VD is less than VS. See, first thing, in an amplifier, we will never let this condition happen, because we have configured an amplifier to extract a gain out of it. So we will never let this condition happen. The moment VD becomes equal to VS, the current through the MOSFET will go to zero. Current through the MOSFET will start going to zero. Yes, its drain terminals will get interchanged, but we will never let this happen, because we have clearly ensured that output voltage is, the output voltage is fixed. You will be connecting a load resistance to that, and you will expect to deliver power to the load resistance. So you don't want drain and source terminals to change suddenly, okay, with input signals. You will ensure that such a condition never happens. If it does, of course, the device is going to behave. Source will be exchanged by drain. So everything, so you can expect a similar behavior. What would have happened now? This is source and this is drain. It will behave the same way. So amplification will happen in the opposite direction. But I'm telling you that this should not be the case, because you have clearly configured your amplifier as an amplifier. So you have connected load resistance to the drain terminal, and you're supposed to deliver power to the load terminal, drain terminal, to the load resistance. For that to happen, you need to have the drain potential to be higher than source. Yeah. Okay. So let me come back. So here you cannot use this. If I ignore R naught, I'll discard this condition. If you consider R naught, you will get a very feeble voltage gain. We'll talk about that at a later stage. Okay, but not good enough. So I'll discard this. Now first, any amplifier, we analyzed three things, if you recall in the previous lectures: input resistance, output resistance, and intrinsic gain. So for a common gate amplifier as well, we'll analyze the three: input, output, and the intrinsic gain. So first I'll start with the input resistance. So first, again, the expressions for the input and output resistances are a little bit more complicated in common gate. So I'll make some assumptions first and tell you intuitively what to expect from a common gate. After that, we'll include the non-idealities and make the analysis a bit more complicated. That's it. So first, I'll assume a load resistance is connected. Now we will find out the input resistance. To find the input resistance, I'm going to look at this point. If I look at this point, assume R0 is infinity. In the first analysis, we will assume R0 is infinity for input resistance. If R0 is infinity, what will be the input resistance? I'm applying a voltage Vi. So I told you guys, if I apply, there is a voltage of Vi across VGS. This is Vi is minus VGS. So can you picturize the current GM VGS, GM Vi flowing from source to drain? A current of value GM Vi flowing from source to drain. Okay. So the input voltage is Vi divided by the input current, which is GM times Vi. So what is the input resistance? 1 by GM. That's it. It is 1 by GM. So if I assume R0 is infinity, if you assume R0 is very large, whatever be the load resistance you connect here, the input resistance will be independent of it. It will always be 1 by GM. See guys, by now when I'm looking into the source, you should automatically think there is going to be a resistance close to 1 by GM. I mean, that should sound intuitive to you by now. If I apply a voltage Vi here, you should expect to see a current GM Vi flowing from source to drain, where Vi here is minus VGS. You should all by now see that. So the impedance will be 1 by GM. That's it. Now this is actually a very low impedance value. So this is like, if you recall your output resistance of common drain is same as the input resistance of common gate, right? Because we are looking into the source in both the cases. Is that fine? If you recall, output resistance of common drain, what was the output resistance of common drain? A common drain configuration is where you are applying input here and output is taken at this point. When you are measuring output resistance, input is grounded and you are looking into the source. What is the output resistance of common gain or out of common drain? What is that? 1 by GM, right? Output resistance is 1 by GM. So I'm just telling you, just for comparison's sake, that this is actually 1 by GM. So this is a very small value. 1 by GM is a very small value. In comparison to what? In comparison to R0. So when you are comparing to resistance of the order of R0, 1 by GM is very small in comparison to that. Next thing, we'll try to find the output resistance. To find the output resistance, I'm going to short circuit the input and find out from here the output resistance. First, let's assume R0 is infinity. If R0 is infinity, what is the output resistance? Infinity, right? Infinity, right? Even if you are changing the drain voltage, there is no change in the drain current. So delta Vd by delta Id will be, this is 0, so it will be infinity. So output resistance is infinity, which is a very good output resistance. It's a very large output resistance. If you assume finite R0, what will be your output resistance? Assume that R0 is finite, your lambda is finite, then your output resistance is R0 itself, because the VGS is 0, so there is no drain to source current. It's only because of R0. So you're looking into the drain terminal, source and gate are grounded, so it is R0 itself. That's it. So your output resistance can be R0 if you include R0, otherwise it is a really large number, it's very large. So this is the second result. Now the third result is intrinsic gain. We'll try to find the intrinsic gain. So for intrinsic gain, I'm going to assume there is finite R0 present. So we'll assume there is a finite R0 present in the circuit. So now picturize the circuit. So I'm going to analyze it intuitively. If I have a voltage Vi, a current II is set in the MOSFET. What will be the value of the current? Okay, one of you are asking, why did I not include RL for Rout? RL, because see, we are finding Rout. Now, Rout is a property of an amplifier. So that's independent of RL. So generally, when you find Rout, that's a property of an amplifier. That shouldn't be dependent on load resistance. Yeah. Okay. So now, if I'm applying Vi, the current flowing in the MOSFET here is GMVI. Now let's trace the path of this current. This current is now going to flow here. reach this terminal. At this point, what is the path for the current? Look at it, I'm just exaggerating here. At this point, it comes here. What is the current here? What is the current flowing in this direction? This is open circuit now. What is the current here? 0, right? There is no current flowing here. So which means this entire current has to flow like this. It will take the path. See, current always has a tendency to take the path of least resistance. So therefore, it's going to take a path this way. And when it does, it's going to create a voltage drop of value. It's going to create a voltage drop of value Gm R naught into Vi. Okay? Okay, so there are two questions. Why is the current 0? Because output is open circuit. If you open circuit the output, there is no path for the current to flow. So therefore, there will be no current. I is 0. Now, I've already discussed why is GMVI flowing from drain to source. See, if you apply a voltage Vi at the gate, so meaning your VGS is plus Vi. If I'm applying, so gate voltage is Vi volts higher than the source voltage, then you will have a current GMVI flowing from drain to source. On the other hand, if you have source voltage higher than gate voltage by Vi volts, then you will have a current flowing from source to drain, because it is actually Gm into VGS. VGS is minus Vi. Actually, you will have a current minus GMVI flowing from drain to source. Invert the sign, change the direction. So you will have a current GMVI flowing from source to drain. Yeah. Okay. So this current traces a path through the resistor R0, and it loops like this. So that will be the path for the current. So what will be the input current drawn here? I. What is the input current? 0. Did you guys see that? Because this current, whatever GMVI is produced, it's going to loop around the circuit this way. It's going to loop around this way. So now can you tell me what will be the output voltage? See, now I will redraw the circuit in a little bit different way. So I think this should be fine now. You are supposed to find out the output voltage V0. That's the voltage at this point to AC ground. Can you tell me what is the output voltage? You know this voltage plus you know this voltage. So can I apply a Kirchhoff's voltage law in this loop? So there is a loop here. So this voltage plus this voltage plus this voltage, sum of the three voltages. So you will get a condition V0 equals Gm R0 Vi plus Vi. So therefore your V0 equals 1 plus Gm R0 into Vi. I'll redraw the circuit. I think it will be more clear. So for example, I'd have, this is the circuit, this is Vi here. I'm asking you to find V0 here. V0 is from this voltage to this, so this is your output voltage, gate is at ground. Look at the circuit now. This is redrawn, the same circuit. I've redrawn it so that it's easier to visualize. Now if I apply a voltage Vi at this volt, you have a current GMVI looping around this way, and the voltage across this resistor R0 is Gm R0 into Vi. So now can you see this node voltage, this V0, this is nothing but Gm R0 Vi plus Vi. So it will be 1 plus Gm R0 into Vi. The intrinsic gain is very high. The intrinsic gain for a common drain amplifier AV is very high. 1 plus Gm R0. Okay. So now we have all the three parameters. What is Rin with R0 represent? I don't understand. I don't follow what you're saying. Okay, what if Rin when R0 is not infinity? I'll come back to that. It's a little bit more complicated. I'll just slightly come back to that. Yeah, I'll quickly come back to that. So now we have all the three results just for quick comparison and analysis. The input resistance is approximately equal to 1 by gm. In fact, it is exactly equal to 1 by gm. Here I made an assumption R0 is infinity. Output resistance is R0. Here I've assumed the source resistance is 0 here, so it is R0. And the voltage gain AV is 1 plus gm R0. Now look at a common gate amplifier. Input resistance is low, Rin is low, and Rout is high. What kind of an amplifier will you use it for? Input resistance is very low, but output resistance is very high. What kind of an amplifier is this? Is that fine? Is that fine with everyone? It's a current amplifier, right? See, for a current amplifier, you want input resistance to be very low because you want to draw all the current from the input. So if I feed a current with a source resistance into a current amplifier, you want all the current to go into the current amplifier, which means your Rin should be very small compared to Rs. Similarly, current amplifier at the output will have its own output resistance. All the current the amplifier is going to generate, you want it to flow into the load resistance. And for that, you need your output resistance to be much greater than Rl. So a common gate amplifier better approximates a current amplifier. It better approximates a current amplifier. So now quickly, I'll try to derive what happens. So is this fine? So this is what I wanted to explain now. What does a common source amplifier better approximate? What does it approximate? Current, voltage, transconductance, what does it approximate? A common source amplifier. For a common source amplifier, input resistance is very large. Output resistance is also very large. It's close to R0. So it represents transconductance amplifier. Okay. Second thing, common drain amplifier. Common drain amplifier, input resistance is very high. Output resistance is approximately 1 by gm. What does this represent? Output resistance is low, input resistance is high. It's an ideal voltage amplifier. It approximates a very good voltage amplifier. Input resistance is high, output resistance is very low. Common gate amplifier, on the other hand, represents a current amplifier, which is why we can use it as a voltage amplifier under certain conditions. It's a current amplifier, it's better suited as current amplifier, but we can use it as a voltage amplifier under certain conditions. So let's quickly discuss that intuitively. Then I'll make the analysis a bit more complicated after some time. So let's see that we have a common drain amplifier. I'm going to terminate it with a load resistance. And at the input, I'm going to assume that the input has a finite source resistance. The input has a finite source resistance. Now we are connecting it to this. So we'll find out the voltage gain. In the analysis, I'm going to assume R0 is infinity because the analysis becomes simpler. Otherwise, it becomes a little bit complicated. I'll come back to that. We will infer some results and then we'll come back to the analysis. So if I apply a voltage Vs, what do you think will be the voltage at this point? What is the impedance seen at this point? See guys, this is how you have to solve your problems as well in your exam. If you know how to calculate impedances at any given node, then it's very simple to solve the problems. So that's why you should know the impedance, how to find impedance. So if I'm asking you find the voltage at this point, if you are supposed to find, let's call this as let me call it as V input, Vi at the input terminal. If you want to find this node voltage, if you know the node impedance at this point, then you can apply potential division at that point. So we just said the input impedance seen here is 1 by gm, right? 1 by gm is the input impedance seen at that node. So now at the input, the circuit is going to reduce to something like this. You will have a source resistance and the resistance at this terminal will be 1 by gm. So this will be Vi. So it will be 1 by gm, it will be a simple potential division, they both are in series, it will be a potential divider. So the voltage will be Vi will be 1 by gm upon 1 by gm plus Rs, which will be 1 by 1 plus gm Rs. This is your input voltage. Now let's come back to this common drain amplifier. Now for this common drain amplifier, common gate amplifier, I've applied a load resistance here. If I apply an input voltage wave, what will be the current flowing in the MOS device from source to drain? GMVI. The same current flows through the load resistance as well. So what is the voltage drop across the load? What is the voltage drop across? What is the voltage gain? Voltage drop across the load. GMVI into RL will be the voltage drop. Voltage gain is GMRL. Now can you tell me what is the overall voltage gain? This is V0 by Vi is GMRL and Vi by Vs is 1 by 1 plus GMRS. So the overall voltage gain is V0 by Vs is given by what? GMRL divided by 1 plus GMRS. This is the gain when R0 is infinity, yes. See, when I say R0 infinity, you should ask me, does it hold true? Generally, what it means is your R0 is much greater than Rs and load resistance. Then I can assume it's infinity in this analysis. If it is much greater than both the load resistance and source resistance, then I can ignore it. But otherwise, we'll see when we include it, the analysis becomes a little bit complicated, but we'll do that later. That's it. So your voltage gain is given by GMRL by 1 plus GMRS. Now let's compare this with a common source amplifier. In a common source amplifier, if I had a load resistance RL and I connected a source resistance here, does the voltage gain depend on Rs in this case? In a common source amplifier? No, right? It has no dependence. The voltage gain was just minus of GM into RL. But here if you see, there is a huge dependence on Rs. Now let's assume Rs is really large. So therefore, your GMRS is much greater than 1. In that case, what do you think this reduces to? GMRL divided by GMRS. Can I say it's approximately equal to normal by Rs? So now if you see this result, what you see here is that your voltage gain is limited by the source resistance itself. That starts limiting your voltage gain. Okay? So that's one problem that we see here. Your source resistance can end up limiting the voltage gain because your Rn is very small. So if you have a very high R0, a stage with very high Rout or Rs, so let's say we have a source with a very high Rout. Rout is very high, or let me call it as Rs. Then you can use a CGA, a common gate amplifier for amplification. Okay, I'm sorry. If Rs is very small, okay, in that case, you can use, when you say Rs is very small, it should be smaller compared to the input resistance of the common gate. Then you can use a common gate amplifier. Okay, yeah. So if Rs is very large, then we have a problem with using a common gate amplifier. Okay, so that's about common gate amplifiers. I have just 4 minutes. I'll take 5 minutes. I'll just start with a discussion of one question. We will then carry it forward in the evening's class, in the night's class. So first, I'll talk about this very important structure called source degenerated resistor. I'm going to add a resistance at this point. Let's call it as Rs. We'll try to find out two things in the presence of Rs. One, what happens? See, previously, if you took a single MOSFET and applied a gate to source voltage of value Vi, we said that the drain current was Gm times Vi. So if I treat this MOSFET as a black box, a 3-terminal black box, I'm applying an input voltage. It has 3 terminals, the input voltage. Then the output current is given by Gm times Vi. Now similarly, if I treat this as a 3-terminal device, I have source degenerated with a resistance Rs, what will be the value of GMVI? What will be the value of transconductance? So if I'm going to treat this, I'll just intuitively explain in today's class and right now, and we'll discuss this in the night's class. So I'm trying to find out, this is say the output node. This is the output node. I'm interested in finding the output current in terms of the input voltage Vi. Okay, that's the goal. So we'll analyze this. I'll call this as, if you see that this can be seen as an open loop system, this can be seen as a system with feedback. Now look at it intuitively. When do you say a system has feedback? If you change your input, there should be some quantity that should be fed back to the input itself. If you take your MOS device, what does the MOS device do? MOS device itself, it operates on the two voltages, the gate voltage minus the source voltage times GM will be your drain current. So your MOS device, if you see, I can represent some, I'll probably show it here. So a MOS device can be mathematically represented as this way. So this is VG from small signal point of view, this is VS times GM will be your drain current. Now what's happening in a common source amplifier with, MOS amplifier with source degeneration? You have an input current, the output current, ID is the output current, that is that's actually going to flow through a resistance RS, that's going to flow through a resistance RS. So now your VS is the source voltage, it's going to flow through a resistance RS, the voltage drop here will be IDRS. So there is some kind of a feedback mechanism in the circuit. Okay, the output current is measured by a feedback network, and this feedback network is now changing or controlling the output current again. Okay, so that's the way the circuit looks like. So I've represented this as a block diagram. So resistor, I have represented as a block diagram. If I know the current through the resistor, the output voltage will be I times R. That's what I'm representing this as. So now can you tell me what will be the closed loop transfer function for this? This is open loop, which was GM. What is the closed loop transfer function? If I ask you, the forward path gain is GM divided by 1 plus A into beta. So if you guys remember from basic control theory, A by 1 plus A beta. So use that. A here is this, beta is RS, GM by 1 plus GM RS is the transconductance. So transconductance reduces. So I'm going to call this as effective transconductance. So this is the effect of connecting a source resistance. If you connect a source resistance at this end, the effect it has is, if I apply a voltage VI, your drain current or the output current is now GM by 1 plus GMRS times VI. Okay, so if you, the moment you connect a source resistance, previously if you see, your voltage VI was entirely dropping across the MOS device itself. It was entirely dropping across the MOS device itself. Now if you see, you know the current GMRS by 1 plus GMRS into VI is the current. So if I ask you the voltage across RS, the voltage across RS will be ID into RS, this current multiplied by RS, so you will get GMRS by 1 plus GMRS times VI. That will be the voltage across RS. So what is the voltage across MOSFET VGS? What is VGS? It is VI minus VS, which is nothing but this. VI minus VS. So can you tell me? VS is given by this. What will be this? What will be the gate to source voltage in terms of GM and RS? So can I say it is 1 minus GMRS by 1 plus GMRS? So which will be 1 by 1 plus GMRS. Now if you see, if assuming GMRS is much greater than 1, if it is much greater than 1, almost all the signal is going to drop across source resistance. So you have two things here. Your MOSFET, the input voltage is now distributed between the MOSFET and the resistance. So VRS, VGS. Now if your GMRS is really great, I mean it's really much greater than 1, in that case, all your input voltage is going to appear across source resistance. Very little input is going to apply, a very small fraction of the input is going to apply across the VGS, gate to source terminal. What advantage do you think does this have? What advantage do you think this has? I've briefly discussed about this in emitter degeneration. What advantage does this have? Exactly. So it creates linearized amplification. Amplification, generally if you take a MOS device, when I say the current is GMVI, this is voltage is VI, I am saying the current GMVI, this is a small signal approximation. This is what we call a small signal approximation. Your actual current is going to be beta n by 2 into Vi minus Vtn the whole square. This is your actual drain current. So if I expand this, it will be beta n by 2 into Vi square plus beta n by 2. I'm sorry, I probably have to write some, okay, but still I think I'll have to write it this way. So what you are doing actually is that there is a quiescent VGS minus Vtn. On top of it, you are applying a small signal Vi. Expand this using the square law equation. If you expand this using the square law equation, you will get a term, call this as A and this as B, A plus B whole square expanded. You will get beta n by 2 into VGSQ minus Vtn the whole square plus beta n by 2 into Vi square plus beta n into VGSQ minus Vtn times Vi. What is this current? What is this term? ID, what is this term? The quiescent drain current. Quiescent drain current. Plus this term. What is the second term here? Beta n V overdrive into Vi. What is beta n V overdrive? Beta n into V overdrive. GM, right? Beta n into V overdrive is GM. So I'll replace this by GM. Now you have a third term, which is your nonlinear current. Ideally, you don't want this term. You, as I told you, linear amplification means you just want to, if you apply a small signal, you want an amplifier to generate a larger signal of this version. I don't want to create new frequencies. For a linear system, output frequency should be same as the input frequency. Only thing, it can be amplified. This is the actual drain current. Yes, yes. This is the drain current comprising both the small signal and the DC current and all of that. Yes. That's what happens in real circuit. But what we do, we just focus on this term. I mean, DC, anyways, we are assuming it's biased, so we remove the DC part. We'll focus on these. In fact, these two are small signal parts. What I'm trying to tell you is that the small signal that you write or when you use for calculating gains, it's an approximation. There is also a nonlinear term present, which we are ignoring in the analysis. But if your input voltage is large, then this will also matter. Okay, this will also matter, and the system will become more nonlinear. So look at this, Vi square will start increasing much faster than Vi if your input signal is increasing. That's the problem with having a large input. Now what are we doing? By reducing the fraction of voltage appearing across the input, I'm going to call it alpha. Alpha is a very small number. Most of it appears across the resistor. Now the drain current, if you see, is proportional to this is, see, look at this. This is what we call as small signal amplification. When I'm writing Vi, I'm already assuming the transistor is biased. And on top of that, you're writing a small voltage signal, Vi on top of it. So there will always be a current GMVI. Look at this equation. This equation is telling you that. Okay, yeah. So fine. So your drain current will then be, given by alpha times Vi into Gm. Previously it was GMVI. Now it's going to be much smaller fraction of Vi. So the nonlinear term will reduce by alpha square, which is a good thing. The amplifier becomes more and more linear. Okay, I'll stop at this point. We will revisit this in the night's lecture, and also we'll discuss some problems. Okay, thank you.